Hello students, welcome back. We have one more topic to go, and that's section 6, the normal approximation of the binomial distribution. This section is written in gray. Does it mean it's not very important or it's too hard? Not really, it's neither. It's just that there's a good chance that I won't be able to cover it in time within week 7 because there are so many other things to cover. If I can't, then I'll simply move it over to week 8 or week 9 and cover it there. No problem. In any case, this topic does belong to lesson 7 in terms of the flow of logic. So I'm going to prepare it here. And if I cannot cover it in time, then I'll simply take this recording and move it over to week 8 or week 9, depending upon the schedule. Okay, let's begin. The normal approximation of the binomial distribution. What is binomial distribution? Does everybody remember? A binomial random variable is an independent repetition of Bernoulli trial, which consists of success, failure, and nothing else. For example, toss a coin 100 times. It's an independent repetition of head, tail, nothing else. The probability is 1/2. There goes an example of binomial. Roll a die 600 times. Ace is success. Anything else, that's failure. So success probability of 1/6, failure probability of 5/6, and repeat it 600 times. That's independent repetition. So there goes another example. How about an earn model? Well, if you repeat with replacement, then that's going to be independent repetition. So it's going to be okay. And about the color, let's say blue is success, and any other color, or non-blue, that's failure, then I get success, failure, and nothing else. That too is an example of binomial. In any case, please remember these two formulae. One for binomial sum, and one for binomial average. For sum, the expected value is pretty straightforward. Roll a die, say 600 times. The success probability is 1/6 for an ace. And how many aces do you expect? 600 times 1/6, so 100. And that's my expected value. That's natural. The standard deviation formula, that's not very natural. So please accept it as a formula. Square root of n, p1 minus p. Memorize it or record it somewhere and bring it back. Now, from here, divide everything by n, then you're going to get binomial average. Each time I roll, there is about 1/6 of chance to succeed. And then the sigma formula, well, you'll simply have to accept it as is. And then, how do you approximate it using normal? Well, I can do that when n value is sufficiently large. If I do a lot of repetition, we have mu and sigma, the expected value and standard deviation. So those two will determine a random variable, a normal random variable. And that normal random variable will approximate Bernoulli random variable if, and that's big if, n is sufficiently large. Let's study that estimation in action through an example problem. Okay, according to Federal Highway Administration's 2007 statistics, about 50.2% of drivers are females. So we have something like this. Probability is about 0.502. So that's success probability, otherwise males. And the repetition, 20 repetitions. I'm a little bit uneasy about this one because the number of repetition is too low. I think the bare bone minimum should be 100 or more. In real life situation, most of the time people use 1,000 or more. But 20, that's too small, so the approximation may not turn out to be very well. But in any case, let's begin. Part A, use the binomial distribution to calculate the probability that less than half the selected drivers are female. Less than half the selected drivers are female. So what do you mean by that? Less than 10 drivers. You see, half of 20 is 10, so less than 10 drivers are female. Here's a formula that everybody should remember. Maybe not precisely, but record it somewhere and then remember to bring it back. You see, binomial n choose k times success probability to the k power times failure probability to n minus k power. So that's the arrangement between successes and failures, and k successes and n minus k failures, total adding up to n. And binomial n choose k can be calculated as n factorial over k factorial n minus k factorial, like this. And that's highly unpleasant computation to do. And then you have to repeat it for how many times? 0 through 9, because you see, you need less than 20, less than half of 20, so less than 10 drivers. So here's a computation. And I did this computation using Mathematica, so I got it like this. But if you use handheld calculator, this is going to be unreachable. With computer algebra system, I can handle it pretty well. Now let's assume that you don't have computer algebra system and you only have handheld calculator. In that case, what do? You cannot do this computation. Instead, you'll have to use normal approximation. So, how do you do that normal approximation? Well, there are two ways. One is using binomial sum, and the other using binomial average. Which is easier? Binomial average method is easier, so let's use that. Okay, the mean and the standard deviation are, just a formula here, the probability is 0.502 and sigma's value is, according to this formula here, square root of p1 minus p over n. Run it and you're going to get 0.11 something. So we have normal approximation by the normal random variable of mu, the mean 0.502, and sigma, the standard deviation, 0.111803. And the normal approximation for less than half the drivers, like less than half. This is what we want. Does it make sense? Probability P is what we want, and that's going to be approximated by normal random variable, normal probability. So Pn, n means normal, and where x is less than 0.5. In terms of average, in terms of proportion, half. All right. X value, mu value, sigma value, we have everything, so we can calculate the z-score and do my computation. And here we go. Let me increase the font a little bit. X minus mu over sigma, n minus center over sigma, and that's a z-score computation. Look at the picture. 0.5 and 0.502 are so close nearby that it looks like it's coming almost toward the center. And if you calculate the z-score and look up the z-table, you're going to get something close to this. And that's extremely close to 0.5. In any case, that is the normal approximation. But then again, there's a bit of a problem here. Let's go back to this. This is a computation we did. Oh, I forgot. This is a probability histogram associated to this computation, by the way. Okay, the dark part is the part that I added, and then light part is not added. So those parts add up to this, and compare this picture and also that computation with this picture and this computation. So this value and that value, they don't resemble very much, and this picture versus that picture, not close. So what's happening here? We did normal approximation, we did get the answer. The problem is, this answer is not a very good answer. It doesn't approximate the real answer very well. Now, if you have no idea what this one is, which you'd have been if you had been using handheld calculator, then you'd have simply used this, and your answer would have been off by a lot. How did it happen? Well, that's because the sample size of 20 was too small. This approximation works when you have large sample size and value is sufficiently large, but 20, not very good. Now, does that mean there's no way to improve this other than just taking bigger sample size? Actually, there is. We did binomial average and then we got an answer, but that was easy to calculate, but not very good. Now let's compensate it using binomial sum method. This is going to be a little bit harder, but it'll produce a bit better approximation. How do you do that? Well, mean and the standard deviation follow from this formula. So here we go. So far so good. NP versus square root of P, NP 1 minus P. Now, less than half of the selected drivers out of total 20 drivers. So less than 10 drivers and approximate like this. Or less than or equal to 9 drivers and approximate like this, which is right. So 10 drivers, less than 10 drivers versus less than or equal to 9 drivers, they're supposed to be the same. But if you look at the normal approximation, because this is continuous random variable, strictly less than 10 versus less than or equal to 10, they're the same. And as for strictly less than, or I should have used less than or equal to there, and then like that. So same as this, just normal approximation. This green, which is same as this because there's no distinction between strict inequality and semi-inequality for continuous random variables. Now look at the first line and second line. They're supposed to be the same because less than 10 people or less than or equal to 9 people are the same because, binomial is discrete. But normal approximation is continuous, so we end up with less than or equal to 10 versus less than or equal to 9, or strictly less than 10 versus strictly less than 9. They're different. So which is right? Whether you use 10 or whether you use 9, we get different answers. So how do I reconcile it? Use your common sense. I'm going to take 9.5. That's what you want to do. So precisely 9 people versus precisely 10 people. If you simply cut through 10, that means you're cutting through a 10th person. You cannot divide a person into 2. I mean, if it is continuous random variable, you can cut it anywhere. But if it is discrete, you cannot cut through a 10th person or the 9th person. 10th person is not included, 9th person is included, then you have to cut through the middle of 9th and 10th people. That's 9.5. So 10 versus 9, so 9.5. So 10 versus 9, we are using 9.5. Will that improve? You bet it does. X value is 9.5, and then mu and sigma are the computation you did before. So z-score is x minus mu over sigma. Turns out like this. And that computation and also this picture comes out very, very similar to what you want. You see, if you use binomial sum with this 0.5 business, then you can make it right. Even with n equals to 20, you can still get a good approximation. That's how the normal approximation works for binomial sums. For binomial averages, you don't do it this way, this sophisticated way, so it's easier, but the trade-off is it's not always very good.